Yeah. No, I'm in the hotel. This millennium. Yeah. You also staying there?
Yeah, I had the complicated. I'll move back there.
Oh, really?
Yeah, millennium is very run down.
Yeah, it's a little bit run down. That's right. Yeah. So they have. So have they updated the dome? In the past, they didn't have a private bathroom.
Yeah, it's shared. Usually shared between two.
Okay.
All right, we're good to go. Remember to turn on your mic.
Okay.
When you're ready.
Okay.
Oh, should be on.
Yeah. It's already on, right?
Okay, yeah, it is on. Everyone's being really loud. You think you're ready to go, huh?
Yeah.
All right, so we're ready to start the next lecture. So this lecture will be from Hong Liu, who's telling us about non-equilibrium effective field theories, hydrodynamics, and emergent supersymmetry. So take it away, Hong.
Okay. Yeah. Thanks a lot for the invitation. Yeah, it's always a great pleasure to be back at the Boulder. Yeah. So as the title suggests, we'll discuss some recent development to formulate effective field theory for non-equilibrium systems. So let me first give you some motivation why we want to do that. So the goal of many body physics, say suppose we are, is to start with some say macroscopic description, and then suppose we know the Lagrangian, suppose we know the exact Lagrangian, for example, electrons in the metal, and we want to predict or explain macroscopic phenomena. Okay. And so this is essentially the goal of the statistical physics, condensed matter physics, etc. And except that this task is almost always impossible if you want to do it directly. Okay, and there's two reasons for that. And the one reason is that typically when you consider many-body system, say quantum many-body system, and the macroscopic description typically contains too many degrees freedom. And it's just too much to track all those degrees freedom. And there's also another second very important reason, is that actually the macroscopic physics is typically a collective, a reflect collective behavior. Okay, so even if you can actually, even if you are very powerful to solve this macroscopic system, in general we are not that powerful. Even if you are powerful, actually, it's highly non-trivial how those collective behavior emerge from those macroscopic degrees freedom. And so those macroscopic variables typically unsuitable for that purpose. It's simply just the wrong kind of variable you want to use to describe whatever low energy physics. So for equilibrium systems, for equilibrium quantities, right now we have a highly successful paradigm to deal with this issue. So this is so-called the Landau-Ginzburg Wilson paradigm, which this is essentially the idea of effective field theory. So what you do is you first you want to identify variables. Instead of starting with those microscopic variables, you want to identify variables suitable for your microscopic for your low energy physics. Okay, namely connectivity loads those variables chi and suitable for the low energy or long distance physics. Okay, and then the second thing in this this paradigm does is that you just identify the symmetries, and you identify the symmetries. Okay, and then you just write down the most general the low energy factor Lagrangian most general. The low energy factor Lagrangian, which describe those variables. Okay, and then you can just express your partition function of free energy So you express your partition function of free energy in terms of those low energy variables. Okay, in terms of those low energy variables. Okay. So the basic idea behind this procedure is just imagine you consider some kind of cutoff scale. Okay. So you consider you have some scale lambda, and those chi's are the variable which are suitable for the physics below some below this scale lambda. Okay. So the chi is the variable which is suitable below this energy scale. And typically, to do this, the ideal situation is that the chi corresponding to, say, some Gapli's variable, which they don't need any, they need very small amount of energy to excite them. And then when you just integrate out those massive variables, those variables, say, with a gap, and then you just get this, when you integrate out in your fundamental theory, you integrate out those massive discrete freedom. Okay? So you integrate out. So SEF obtained by integrating out the massive degrees freedom. Okay. You got the massive degrees freedom. And so that is the basic idea. And of course, this procedure in general cannot be done directly. If you can do this directly, then you essentially have solved this theory. Okay. So in general, this procedure cannot be done directly. So that's why you need the second and the third step, and then you write down the most general possible Lagrangian. You parameterize your low energy physics, and then you determine the parameters in this Lagrangian from, say, small number of experiments, and then you can predict a phenomena for larger set of experiments. Okay. And so this paradigm has been extremely successful. The reason it's successful, it's clear just from the procedure itself, because by focusing only on chi, you have avoided these two essential defects from starting from macroscopic physics, because you have only concentrated on very small number of degrees freedom, which are suitable for the low energy physics. Okay, for the physics you are interested in. Okay, for the physics you are interested in. And so most of our understanding of condensed matter systems are based on this paradigm. For example, superconductors, superfluids, magnetism, phase transitions, etc. And also in particle physics, in the standard model, the proper way to think about standard model is also should be thought of as a non-effective non-effective description, say, of some unknown UV physics. And of course, for the case of the standard model, we are considering states near the vacuum. And here, in general, we are considering, say, highly excited states. Okay. So, any questions? Good. Okay. But for non-equilibrium problems, we are not so lucky. Okay. For non-equilibrium problems, we are not so lucky because non-equilibrium is actually much, much richer than equilibrium situations. And actually, most phenomena in life, actually, in reality, are non-equilibrium processes. And the one immediate difficulty with the non-equilibrium is that in the non-equilibrium situation, we don't have such a quantity such as free energy. So in the equilibrium physics, the nice thing about free energy is that this quantity essentially, so when you put the appropriate sources here, this free energy essentially captures all the equilibrium physics. Okay, but for non-equilibrium physics, there's no such quantity which is analog of the free energy, which say captures all the non-equilibrium physics. And so just the starting point, we already know. It's already not clear what should be the starting point. You write down your low energy effective theory, and what this low energy effective theory should compute. And even this question is not clear for the non-equilibrium situation. Okay. And the goal of my lectures is to show you actually one can actually develop a non-equilibrium. He said this kind of philosophy actually can be applied to the non-equilibrium situation, and to develop effective field theory, which actually can treat a very large class of physical systems. Okay, a large class of physical systems. So first, if we want to develop, say, some kind of apply this paradigm to non-equilibrium physics, again, you have to think about two questions. First is that what kind of quantity you want to compute. Okay, is that what kind of observable you want to use this low energy effective theory to describe. So this is, of course, the first question. And the second question is what are the low energy? What would be the low energy degrees freedom? Okay. What will be the low energy degrees freedom? So now let me just make some comments regarding what are the low energy degrees freedom. Okay, for the general non-equilibrium situation. Okay, and so we normally, so when you go to non-equilibrium, the story is a little bit complicated because to say something which is gapless is already not a very precise word anymore when you are in a non-equilibrium situation, because often your Hamiltonian depend on time, the energy is not conserved, etc. Okay, and energy may not be conserved, and so we often sometimes also use the notion called slow modes, slow variables. So this so heuristically, these are kind of the variables which have very long lifetime, okay? Which have very long lifetime. And so if you're interested in the low energy and the long distance, long time physics, and then these are kind of variable you should be focus on, okay? You should focus on. And the reason we emphasize slow is that in the non-equilibrium situation, for example, for a system, even in the finite temperature, you can have gapless excitations which are very short-lived, okay? They have very small frequency, but they actually are short-lived. And for those kind of degrees freedom, then we should not worry about them because they come and go, and you will not observe. So they will just essentially they can be integrated out because they have very short lifetime. Okay, and so here we are emphasizing the slow. Yeah, for example, in the CFT, so if you say put the CFT at finite temperature, then all those gapless degrees freedom in the CFT will be excited. And those degrees freedom will flowing around in your finite temperature, but those degrees are not coherent. And they come and go. So when you consider the non-equivalence process for CFT at finite temperature, you should integrate also those degrees freedom out. Yeah, even though they are essentially gapless.
But
yes.
You have to restrict attention to models where you can separate these scales?
Yeah, that's right. Okay. That's right. Yeah. Exactly. Yeah. So for example, in the conformal field theory, in the CFT case, the scale which typical lifetime will be 1 over the temperature, and so you want to consider time scale much longer than that. Good. So now let me just mention a little bit about what are the typical degrees freedom. So turns out actually one can actually even without going into any specific details, only without looking at any specific system, you can already say a lot about the slow variables in the general non-equivalent process. Okay. So in general, there are two types of slow variables. Okay, there are two types of slow variables, and the one type are associated with conserved quantities. Okay, and this kind of slow modes are actually are universal. They actually exist for all many-body systems. Sufficiently excited many-body systems is because essentially any system which have conserved quantities. And to see that the conserved quantities always leads to slow modes, and it's very simple. So let's consider we have some long wavelength excitations. Okay, suppose this is the equivalent value, and so imagine this is some direction, and this is the value, say of some. The value of some variable, and if this variable rho is not conserved, okay, and then it can relax everywhere. So even if you have very long wavelengths, typically these kind of excitations can have a very short lifetime. Typically, they will relax at the typical time scale of the collision scale. Or just mean free time, or say if you have say in the simplest system, say in the quantum in the scale invariant in the CFT, that would be 1 over temperature. Okay, but now if you have conserved quantities, so for non-conserved quantity, typically you would expect in the medium the lifetime would be very short. So 1 over t here I consider to be a very short time. I always consider the time scale much greater than 1 over t. But if you have a conserved quantity, so if suppose this rho is conserved, say the charge, say of some say some conserved charge, and then this cannot be, then this rho cannot be destroyed locally. Okay, it can only be the equilibrium can only be achieved via transport of the rho. Okay, so the positive charge then should be transported into the negative charge region, and then eventually they will achieve equilibrium. And now in this case, so here you can only relax by transport. Okay. And now if you take your wavelengths to be longer and longer, and obviously take a longer time for the transport to make it into equivalent situation. So that means this kind of excitations will always have very long lifetime. Okay, so this always leads to long-lived mode. Okay, they always lived long-lived mode. Yes.
Does that mean you generally consider like the associated current as your quantity, or do you look at objects that are charged under whatever quantity?
You look at the current itself, the charge density itself, okay. Because only charge density is conserved. Yeah. Yes.
Sorry, one more time, dumb question. Why is the intuition that these should be long-lived modes?
It's because they can the charge cannot be destroyed locally because they're conserved, and so they can because the total charge of the system is the same, and if you want to achieve the equivalent situation, say everywhere to be the same charge, and the only way is for the excessive charge here to go to here to fill the deficit of the charge, and if this distance, which is typical wavelength, is very long, and then the time takes infinite time. So if lambda goes to infinity, and then the relaxation time will also go to infinity. Okay, because you need to transport the charge from here to here.
But couldn't you have fast transport?
Everything is constrained by speed of light. Yeah.
But for like a thing in the lab, I don't think the speed of light is particularly important, is it? So for the thing in the lab, you may have sound velocity or some other characteristic velocity. There's always finite velocity. Yeah, for the transport. Yeah, for example, for this room is controlled by the typical molecular velocity. Good. So you're assuming local physics only.
Okay. That's right. Only assume local physics. That's right. Good. So that tells you that whenever, so this is the key, whenever you have conserved quantities, okay, you always have slow modes, okay, and so this is universal, okay, so this kind of universal, so this is a little bit like the Goldstone modes when you have symmetry breaking, okay. There, once you have symmetry breaking, then you always have gapless modes, and here, whenever you have conserved quantities, there's always in the medium, there are always the slow modes associated with conserved quantities. Okay. Good. Okay. Then the second type of slow modes, then they are non-universal. They are non-generic. They're specific to individual systems. So, for example, you can have situation if you are near the phase transition. Then there's something called the critical slowdown happening near the phase transition. Then the order parameter, and then can also be a slow mode. Okay. So the order parameter can be a slow mode. And say if you have a symmetry breaking phase, then the Goldstone mode can also be. The Goldstone boson can also be a slow mode. And say if you near a Fermi surface, if you near a Fermi surface, and then there are always slow modes come from the fermionic excitations near Fermi surface. Okay, and etc. So those modes are non-generic, okay, depend on specific systems. And for general system, we cannot be a phase transition. Say we don't have some symmetry breaking, and we don't have a Fermi surface, and essentially the only thing left are the only slow modes left at a very long distance are those associated with the conserved quantities, okay? And those associated with conserved quantities, then they are the only ones, okay? Yes. Yeah, that's right. Yeah, near the second order phase transition. That's right. Yes.
What's the difference between this one from the
Sorry, say it again. So, if I heard you correctly, the order parameter does not have to be associated with any conserved quantities. For example, if you consider IC model, say IC model near the critical point, and then you will have then the order parameter, the relaxation of the order parameter near the critical point will be very slow, and that should be incorporated in your low energy physics. Yeah, that dynamics, that relaxation dynamic should be included in your low energy.
You are talking about the fixed condition
this can be equivalent phase transition. So this says the near equivalent phase transition, but you consider, for example, time-dependent correlation functions for equivalent phase transition. And there, for example, if you look at, say, if you have phi t, phi 0, say for Ising order parameter, and then this will have some power law near the critical point. And so that indicates this critical slowdown, etc. And so that indicates the phi, the order parameter, should be part of the non-lift mode.
What is it precisely that makes the order parameter slow as opposed to other gapless modes?
It's because of the it's because you are near the critical point, and it's essentially due to the scaling behavior you approach a CFT. Yeah, essentially the Euclidean part is described by CFT, and then the time is also controlled by that kind of dynamics. Good. Okay, so for generic systems, essentially these are the only ones. Okay, these are the only ones. And yeah, of course, the theory, the low energy theory governing those modes has been well known for many years, hundreds of years, if not thousands. So these are the hydrodynamics. Okay. So the theory governing conserved quantities, say low energy theory, conserved quantities, essentially just hydrodynamics. And somehow, where are the other chalks? Oh, yeah, that's right. So the hydrodynamics, and those slow modes are just what we normally call the hydro modes. Okay, so the slow modes are we normally call the hydro modes. The hydro modes. Okay. So essentially, the hydrodynamics is the universal low energy effective theory for essentially all many body systems. Okay, for all many body systems at sufficiently long wavelengths. So that's why actually hydrodynamics essentially is ubiquitous in physics. It governs physics in many different subjects, from our real life, a hurricane, weather, to a star formation, galaxy formation, cosmology, evolution, etc. And also the hydrodynamics has played a very important role in modern condensed matter physics. And for example, recently people discovered that the graphene, say electrons in graphene, they actually move like a fluid. And rather than naively electrons in the metal, they move ballistically, say like billiard balls. But actually, people discovered that in the graphene, actually electrons move like actually fluid. They can go around the barrier rather than collide with the barrier. Okay, and also there people have many strong suspicions that maybe in certain strongly correlated materials, may even including say high DC superconductors, hydrodynamics may also play a very important role in the electronic physics there. Okay, and also in heavy ion collisions, when people collide heavy ions at Brookhaven and LHC to form this so-called quark-gluon plasma, and so this droplet of quark-gluon plasma, they essentially behave like a fluid. Okay, they behave like a very good fluid. And also in the ADS-CFT correspondence, the hydrodynamics is mapped to the gravity, and the classical equation motion of hydrodynamics is mapped, say, to the Einstein equation. and etc. Okay, and also physics of the black hole plays a very important role in these relations. So this hydrodynamics is essentially everywhere, and actually may also be related, may also be underlying, say this kind of quantum many-body chaos Juan was we've been talking about. Okay, so despite this long and glorious history of hydrodynamics, but hydrodynamics still have some very important defect. It's because it's still formulated, after so many years, it's still formulated as a phenomenological theory. Okay, it's still a phenomenological theory. So you actually need to, many input of this theory needs to be put in by hand. Okay, need to be put in by hand based on physical intuitions, etc. And they're not derived from first principle. And so this is one thing. So you just say the first is not from first principle. Not from. So I will make this more precise a little bit later. And the second very important defect of hydrodynamics is that it's formulated as an equation motion. So again, I will review this a little bit more explicitly later. But if you have studied some high school physics, you know hydrodynamics are equation motions. So that means you cannot treat fluctuations systematically. Okay, cannot treat fluctuations systematically. Okay. But fluctuations are important for many aspects of physics. So for example, in the context of phase transition, so before Wilson, people were able to treat the phase transition, say, using mean field. And only after the Wilson, we can actually treat the fluctuations of all the parameters, fluctuations, those things properly, and then you see then you can describe a whole rich phenomena from that. Okay. And so the defect of hydrodynamic is actually cannot treat the fluctuations. And so you always, it's always like some kind of mean field approximation. Okay, it's always like some mean field approximation. And so now let me just mention it quickly. So what we want to do is we want to develop the hydrodynamics. So we want to really develop a low energy effective field theory for conserved quantities as a genuine low energy as a genuine effective field theory in the sense of this Nando Ginsburg-Wilson perspective. Okay, and that way, then we should be able to treat the fluctuations systematically. Okay, we should be able to treat the fluctuations systematically, and then we should also be able to explain many phenomenological features. Phenomenological input which you have to put in by hand in hydrodynamics itself. Okay, so just to give you a little bit flavor, so let me just quickly mention a few cases which the hydrodynamic fluctuations has not been important. Okay, has not been important. So the first example is what people normally call non-equivalent phase transitions. So this is a place which hydrodynamic, to have a theory of fluctuating hydrodynamics could be very could be fruitful. So let me give you a simple example of this, which we actually many of you so one of the simplest example of this non-equivalent phase transition, this is thing called the Rayleigh-Ballard problem. So this is a very simple system. Say you consider you have a tank of water, which you say you can do it at home, or consider, say, just some air, just some fluid, put in between two plates with different temperature. Okay, so suppose T2 greater than T1. Okay, So you heat from the bottom a little bit, okay, or you cool in the up. And if the temperature difference is small, so at the beginning, this system just develop a gradient of temperature from the bottom to the top, okay? But we know, just from your experience of boiling water, that now if the temperature difference is big, and now they will start having the convection, okay? The system will have the convection. Okay, there will be convective flow between them. And the transition between these two is like some kind of second order phase transition. Okay, it's controlled by hydrodynamic fluctuations. There's some kind of hydrodynamic instability and controlled by hydrodynamic fluctuations. And so far this is a very old problem. This is a 100-year-old problem. But so far people mostly just treat it as a mean field approach to treat this problem. And so potentially if you have a series of fluctuating hydrodynamics, then you can treat it actually just using the Wilson, as Wilson treated the equivalent phase transition, and maybe now we can treat this kind of problem. Yeah. So a second example, which the hydrodynamic fluctuation may become important, is that the transport, we may see the rounding of the transport parameter. So we scale. So when you write down hydrodynamics, the inside the which appear as parameter of hydrodynamics, including viscosity, conductivity, etc. Okay, and so they are normally. So there are parameters in your hydrodynamics, and from our modern point of view, there are couplings in this low energy effective theory. Okay, in the low energy effective theory, and when you treat this hydrodynamics from equation motion, essentially with a mean field, and then they are just constant; they don't do anything. But now, if you include the fluctuations, and then just add ordinary couplings in your quantum field theory or statistical field theory, then they will run with scale. Okay. And they will actually depend on your scale, and such kind of running actually can be important. Such kind of running can be important. So this is also related to something people call non-time tail. So if you look at, say, the 2-point function which controls the conductivity or viscosity, and then you will see some kind of a power law tail dependence on time, etc. Okay, and in certain situations, for example, near the phase transition, near equivalent phase transition. Near a certain equivalent phase transition, it can happen. For example, this conductivity, when you run to the low energies, okay, when you run to the large distance scales, actually this can actually diverge. Okay, can actually diverge, and then that actually can affect many other important quantities, say like dynamical exponents, etc. And so this just gives you an example that such kind of running of transports can actually be very important. And so far, this kind of thing, again, I only treat it at the phenomenological level. Okay, phenomenological level. So so under the third example, which such thing can be useful, is Hyberian conditions. So in Hyberian conditions, people create this quark-gluon plasma, which are some very tiny balls of quark-gluon plasma. Okay, it's say the size is about 14 Fermi, and for such a small system, statistical fluctuations can be important. Okay, and so if you really want to properly to describe experiment, you may need to include the such kind of hydrodynamic fluctuations. And also in Hyberian collision, a very important near-term project is to search for this so-called QCD critical point. So if you look at the QCD phase diagram, there's a temperature and there's a chemical potential. Baryon chemical potential, and it's believed that there's a second order critical point somewhere in this phase diagram. And we don't know where it is, And if you want to scan around this critical point, and the way you see the signature of this critical point is to see the fluctuations, okay? Because near the critical point, fluctuation become very big, and that will be the signature. Say you have found the nearby the critical point. Yes.
Does lattice QCD see this transition as well?
No, lattice QCD is not very easy to see because this is a finite chemical potential, so you have a sign problem, etc. Yeah. So to understand hydrodynamic fluctuations would be very important. Say for scanning such kind of critical point. Yes.
I'm sorry, I have a
Yeah.
question. What do you mean when you say hydrodynamics and hydrodynamic behavior? If field theory is the physics of waves, what does it mean that my waves are acting like a fluid now as opposed to just generic field theory? Like, and I call this scalar field like a mass field or conductance field, something like that. Like, what restrictions on the equations do I have? Like, what equations do you look at and you say, oh, that's hydro, not just generic field?
Oh, so I will explain that. So the first, so this is the question we will explain. You will see very explicitly later. You will see very explicitly later. Yes.
I just have to point out that if you draw these diagrams of, say, that you're going to go to the street of these at the critical point, but the experiment says, no, you are not in a equilibrium phase diagram.
Yeah, that's right.
More appropriately, maybe it's the thing of space, high-dimensional space, and you have a trajectory. I mean, maybe it goes to this point and it's just close to equilibrium, but you're never actually going to be.
Yeah, exactly. Yeah.
I think that might be an equilibrium phase condition. There's a certain chance that you have a non-equilibrium problem and it's not clear to me that you would get a non-equilibrium signature of this.
Yeah, sure, exactly. So the realistic to probe this critical point is a very, very complex physical problems, but fluctuation will play a key role. Fluctuation will play a key role. There was another.
Yeah, I have just a very simple question. I don't understand why conductivity will run with scale. I have the actual while I look at different scales.
So that's a very good question. So the example which I have in mind. So this conductivity is a coated conductivity. It's a conductivity for some conserved charge. So one example of this happening is a binary fluid, which you have two kind of fluid, and then the phase transition corresponding to from equal density to the density not equal. And so this conductivity is conductivity for the difference of the that density. So it's not the genuine conductivity. Yeah, it's some kind of observable of that theory. Yeah, it's I say it in the generalized sense. Yeah. Good. Okay, so and then speculating a little bit. So from ADS-FT, the hydro fluctuations will map to essentially the quantum gravitational corrections. Essentially, from the gravity point of view, these are corresponding to the fluctuation of the metric. Okay, a fluctuation of the gravity itself. And so hopefully, maybe by understanding the hydro, and then from the also from ADS-T perspective, then that can also give us a deeper way to understand, say, the ADS-T correspondence, or maybe the gravity, etc. Okay. So of course, there are many things one can still say. Let me just finally mention something very speculative. Very speculative is that to have such a theory to really formulate the hydrodynamics as a general knowledge effective field theory may be also useful for treating the problem of the turbulence. So turbulence, of course, has been a well-known problem for many, many years, also more than 100 years. And so people in the 50s or 60s already observed somehow the best way to think about turbulence is not to track a specific turbulent flow, okay? Not to look at specific turbulent solution, but looking at the class of turbulent solutions, okay? To do some kind of ensemble average of the in the space of turbulent solutions. And then they observed already in the 50s and 60s in the Soviet school, they they were shocked by that the kind of technique they used to describe turbulence is very, very similar to the kind of technique we use to describe quantum field theory. Exactly the thing we do in the quantum field theory. So people have been searching for many, many years that somehow maybe there's a quantum field theory behind the turbulence, okay? Behind turbulence. So now if you now really treat the hydrodynamic as Lorentz effective field theory, and now maybe you can imagine maybe turbulence can arise at some kind of a fixed point because of turbulence have scaling, etc. Maybe it can arise at some a fixed point of this kind of statistical field theory which we use to describe hydrodynamics. And then, so that maybe provide some additional technical tools which we can tackle this problem. Okay, so this is just some general motivations for understanding this hydro as effective field theory. So now let me just now say my plan. So the next thing I will do is I will describe the general setup for formulating a class of non-equivalent effective field theories. Okay. And then I will just apply this to develop a non-equivalent EFTs for conserved quantities. Okay, for conserved quantities, and in particular, for conserved quantities of a general many-body system. Okay, of a general quantum system. So we always consider a system is in the medium. Say it's a highly excited system, not say near the vacuum. Okay. And then we will see once you formulate this theory, then hydrodynamics then arise. Then standard hydro just arise as equation motion. So once you have formulated properly this knowledge effective field theory for conserved quantities, and then you find that the traditional hydrodynamics indeed just arise as equation motion of this theory. Okay. And but this theory will be able, in particular, even though this is a Lagrangian field theory, actually it incorporates dissipation and dissipative effect, retardation effect, etc. Okay, fluctuations, etc. And so in this approach, so we will actually find that the classical, in the sense I will define later, the classical hydro is mapped to a quantum field theory. Okay, so essentially statistical fluctuation here is described by some kind of described by a quantum field theory. So this is very similar to what you do in the equivalent field theory. Say there a classical statistical partition function then can again be described by a field theory. Yeah, like Ising critical points. And you can also, in principle, include the quantum. Generally, in quantum hydro, this is a little bit more tricky to define. And then we see some hints that this will be some kind of deformed quantum field theory. So this theory already have H bar. So this theory already have some kind of H bar which captures the scale of the classical fluctuations. Say this H bar is like 1 over the entropy density, okay, which characterize your standard statistical fluctuations. But now we see actually, but now if you're including a genuine H bar, so this theory have to be further deformed to put in another H bar, and so this is quite yeah. So so this is just and then we will see, and based on this formulation, then we we see actually there will be a, then I will give a new proof of second law of thermodynamics. Okay, a new proof of second law of thermodynamics. So traditionally, the second law of thermodynamics has been proved using so-called Boltzmann's H theorem. Okay, Boltzmann's H theorem, but Boltzmann's H theorem only applied to dilute gases, and so this will be so this proof actually will apply to more general class of systems. Okay, a more general class of systems, and so I believe actually this approach may actually provide some kind of hydrodynamic approach, potentially a hydrodynamic approach to quantum informations, say to those reduced density matrix, say for quantum systems. And finally, if I have time, then I will show that generic system. So one key thing here, one key concept one key thing I will introduce here is a notion, is a precise mathematical notion of local equilibrium. Okay, so when you consider such a kind of long wave fluctuation, when you consider such a kind of long wave disturbance, okay, and then at some short distance scale, at some distance scale which much larger than your UV cutoff, but much smaller than this wavelength, then the system should be in local equilibrium. Okay, and so this is the heuristic way to say this must be in local equilibrium. But now the key question is how do we incorporate this local equilibrium concept into effective field theory? Okay, in the standard hydrodynamics, this is put in by hand. So in the standard hydrodynamics, this is put in by hand, and this is the key of hydrodynamics. In the formulation of hydrodynamics, this is the key. You have to impose that the system is in a local equilibrium. But you cannot put in by hand when you formulate it as effective field theory. And then we find actually there's a precise mathematical way of doing it. And actually, you do it just by importing a Z2 symmetry. Okay, turns out that this there's just a Z2 symmetry we can do this for you. Okay, a Z2 symmetry does for you. And then you can show that for any system with this local equilibrium, with this Z2 symmetry, okay, there's always an emergent supersymmetry. Turns out the system is supersymmetric. Okay. It turns out the system is supersymmetric. Okay, so this is my goal, but I'm to cover those topics, I may not be able to reach all of them. So we will see how far we can go. Good. Any questions? Yes. Yeah.
So maybe
Yeah. That's very interesting, indeed. So yeah, hydrodynamics seems to be valid, much more general. Yeah, in much more general situations. Yeah. So making this thing precise as a Z2 symmetry in your effective field theory, then we can imagine drop it and see what happened with it. Or replace it with something else. And actually, there are many interesting systems. For example, this KPZ systems, which does not have local equilibrium, which is not in the local equilibrium in the traditional sense, but somehow they have a very nice infrared fixed point, etc. And anyway, yeah. So indeed, that would be a very interesting question. Yeah, this would be an interesting question to explore what replace this kind of Z2 symmetry. Yes.
Is the supersymmetry local?
Yeah. Supersymmetry is a global one. It's not a local symmetry. It's a global supersymmetry.
So it merges into a global.
Yeah.
Can you have a local?
You can have it. You can have it. There are two formulations of it. There's one version which if you don't fix the gauge, If you don't fix some local symmetries, then supersymmetry looks like local. But then you can fix some local symmetries, and supersymmetry will be a global. So essentially, it's like a global supersymmetry. Yeah. So what this does is that you have two fermionic charge. The anti-commutes into translation in the time direction, but the shift is given by the local temperature. It's given by the local temperature. And since the local temperature depends on the space-time, so it looks like it's like local SUSY. But then you can actually fix some other equilibrium and make that local temperature to be constant, and then the supersymmetry become like global. Good. Okay. So now let me just go back to do the first one, or try to formulate. So now I try to answer the question: what would be the object we should look at to replace this Z? Okay. So what object we should look at to replace this Z?
So just to follow up on this question,
Yeah.
In one frame it looks like local supersymmetry. Do you get local supergravity too before gauge fixing?
Yeah, I don't know. It sounds like that, but that theory we have not systematically studied. We just have written it down. So yeah, it does like that. Yeah. Yes.
Yeah, after you have this measurements for symmetry, I am trying to do some
That I don't know yet. That I don't know yet. That's our hope. Is that this supersymmetry will help you to say find the infrared fixed point of this large class. Yeah. So the key we want to one of the goals to formulate this kind of theory is you want to explore what are the infrared fixed point of those theories. They may tell you some new physics, etc. And so the supersymmetry may help that in that aspect. Yeah. Oh, I should also say there's of course many papers, including our own papers and other papers on this subject. So normally, do people put the references on this wiki page, or what is the standard practice?
As much as you want, please.
Yeah.
Put more than you think you should put there.
Oh, okay, good. Okay, so I will not write references here. I will put the wiki in the wiki page. Yeah. So let me just mention some of my own collaborator. It's Paulo. Rioso, Mike Crossley, and Pingao. And also I'm working with Srivatsan Rajagopal. Good. Okay, so now let's talk about what should replace this this partition function when you go to line equilibrium situation. Okay.
15 minutes left.
Oh, only 15 minutes left. Okay. Yeah. That makes me feel like a beginning graduate student, because people say beginning graduate student always give too long introductions. Okay. So now let me talk about the formulation of the how we should replace this. So this is something called the closed time path. Okay, so so in partition function, yeah. So normally when you do the partition function, you just integrate. So you integrate your fundamental theory on the Euclidean Say this is your fundamental theory. Then you just do the path integral on the Euclidean manifold with periodic time. And so particle physics, we are often interested in, say, S matrix, etc. So which is the scattering amplitude. So you start with some initial state, and then what you do is you do a path integral from minus infinity to plus infinity, and then so the path integral then give you the map from the initial states to the final states. Okay, give you the transition amplitude from the initial state to the final state. And so these are the things we are familiar with. But if you are interested in the non-equivalent dynamics, then the object you are interested in is a little bit different. Is the typical observable we are interested in would be, say, correlation functions in some density matrix. Okay, so this density matrix, of course, can be a pure state, and this is just some states. Okay, this is just some macroscopic state. Okay, so we are interested in the by macroscopic state, which is a state which is a medium. Okay, it's not near the vacuum. Okay. And so this is the kind of object we are interested in. And so this tells you actually now when we look at the path integral formulation for this kind of questions, we need to think a little bit differently. So if you look at the evolution, so if you look at the time evolution, say, of a density matrix, it evolves as follows. Say evolves t0, say rho 0. Suppose rho 0 is the density matrix at some initial time, and then you dagger t0. Okay, so that means, yeah. Let me use the tf, ti. So the real, and so if you write this in the path integral. And then you have something like this. You start with the initial state rho 0, and then you evolve in time, which is the so if it then you can use the standard technique to translate the evolution operator in terms of path integral, and then you essentially have two lines: one corresponding to u, which propagates forward in time, and one corresponding to u dagger, which propagates backward in time. Okay. Okay, propagate backward in time. So now the simplest thing, okay, now the simplest thing you can do, okay, now the simplest thing you can do is just to trace, okay, just consider taking the trace around, say, at the t equal to tf, okay, and then when you insert the operator here, okay, then that will give you a class of operators, okay. So that will give you a class of operators. So that will give you a class of observables. Okay. So you trace it, and now since this is run in the real time, and now this gives you a class of real-time observables. Okay, give you a class of real-time observables. Give you a class of real-time observables. So it's convenient to write this in terms of the generating functional. So you can define this as a generating function as following. So z phi 1 phi 2, initial phi 1 phi 2 is defined to be trace rho 0. Then you do path ordered. The exponential I phi 1 o dt minus, sorry, I don't have enough space. So this path ordered times exponential I phi 1, so path ordered phi 1 o 1 phi o dt minus I phi 2 o dt. Okay. So that means when you want to insert operators there, so the simplest way, just introduce a source for some operators, as O is some operators that you are interested in. So the O is the operator you're interested in. Then you just put a different source for that operator on this two leg of the contour. Okay, the two leg of the contour. And let me put O1 here. O1, O2. Okay. And the minor sign, so let me just make some remark on on this expression. So O1, O2 actually are the same operators. So 1 and 2 just only distinguish the location, okay? So 1 and 2 only distinguish location. So 1 means inserted in the first leg, 2 it means inserted in the second leg, okay? So now if you put different source, phi 1 and phi 2 on different legs, and then when you take derivative over this source, and then you can get the operators inserted on the different location, okay? So that's what we want to define here. Yeah, and then this minus sign, it just because the minus sign is from the time from the reverse the contour, okay? Just from the reverse contour, okay? So I only written time integration here. Of course, you should imagine the space integration too. Okay. So by closing this, by taking the trace at one end and then you insert operators, this gives you a class of observables. So this class of observables are typically of this type. So when you take derivatives, when you take derivative over phi 1 and phi 2, when you take derivative over phi 1 and phi 2, then you just get the typical observable. So the typical observable is T, anti-ordered. So on the second, so when you, because anything from the path integral is ordered from the path integral. So on the second leg would be anti-time ordered, and in the first leg would be time ordered. Okay. So the typical observables would be like this: O2, T1, O2, say Tn, and the T, O1, say Tn plus 1, O1, T, O, just now you can only O. Yeah, O1 and 2, yeah, O1 and 2 just used to distinguish whether it's in the same leg or the second leg, okay? And once you write in terms of correlation functions, then you don't have to put this 1 and 2, and then say to Tm. Okay? So this will give you a class of observables like this. On the first leg, it's time ordered. On the second leg, it's anti-time ordered. And anti-time ordered always put before the time ordered. Okay? Yeah, that's just what that contour tells you. Okay? I'll give you a class of observable like this. And you can consider more complicated situation. You say, oh, instead of looking at these two, instead of that, I can do rho T F, say to be U, rho 0, U dagger. Okay? So I can separate U into two steps, and then I can do a contour like this. Okay? Or I can put more U here, then I can get more lines, always even number of them. Okay? So this corresponding a class of them, which I just stop at 2U, and then I only have two contours, and that gives you this class of correlation functions. Okay, this gives you this class of correlation functions. So it turns out that this class of correlation functions are precisely what is relevant for most physical problems. Okay, relevant for most physical problems. So now let me explain that. So for that purpose, I have to do a slightly transformation. So I will introduce a new notation. So I will introduce phi r equal to 1/2 phi 1 plus phi 2. So remember, phi 1 and phi 2 are the sources of the two different legs. And then I introduce the difference of them, phi a, phi 1 minus phi 2. And similarly, I introduce OR equal to 1/2 O1 plus O2. And OA equal to 1/2 equal to O1 minus L2. Okay, so this is okay. And then, so you should view this index as index on the O. Index on the phi are generally indexed because phi 1 and phi 2 are different. And the index on the O should always be interpreted as indicating the location on the contour, okay? Location on the contour, which give them the orderings, okay?
So what does that R and A stand for? What does R and A stand for?
Yeah, that's right. Symmetric and anti-symmetric.
But why R?
Yeah, this is the traditional notation. Yeah, if you are the first person to do this, you can introduce some other crazy thing for this. Okay. So now with this, then this generating functional can be written as phi r, phi a. Then you have something like this, trace, again path ordered. 0, then path ordered. Then you have exponential I OR phi a plus OA phi r. Okay? OA phi r. And now you can take derivatives with phi. Okay, now you can take derivative with phi. So now you can take derivative with phi r and phi a. Then you get this kind of correlation functions. Okay, so you get say G R R A. This kind of correlation function with index R and A with say W, say phi. So R will corresponding to take derivative over phi a because this is the and then phi a and the phi r. And phi r, of course, all at different locations, like this. So this is OR, OR, OA, OA, etc. Okay? So this will give you correlation functions like this, labeled by this RA. Okay, R and A corresponding to, you consider the correlation function of OR, OA, then that corresponding to take derivative with, back to the opposite symbols. Okay? Opposite symbols. And now, so the key advantage of using these spaces is the following. So now let me give you an example, okay? So now let me give you an example. So these are just, again, when you look at this, OR, you just replace it by O1 plus O2, and then you order them according to 1 and 2, okay? So now let me give you an example. So now let's consider the simplest case, just a 2-point function, GRA, T1, T2. So this gives you, so again, let me just put some I here, which I'm not careful here. So this gives you a path ordered OR, T1, OA, T2, okay? So by definition is that, okay? By definition is that. So now let's look at what this means, okay? So this I just replaced by 1/2 O1 and O2. So this become I path ordered. So O1 T1 plus O2 T1, and then O1 T2 minus O2 T2. Okay? Minus O2 T2. So now I just write, then you just write each term. So when O1, then this just should be time ordered. If you just O1, which is on the first leg, should be time ordered. So I just have time ordered O1, T1, and OT1 and OT2. Okay? So this is from first one. And the second term will be minus, which this is O2 and O1. So O2 should always come from O1. So this become a Whiteman function, O2, OT2, O1, OT1. Okay? And similarly, this one just gives you plus O2, T1, OT2. And then the last one is OO2, then that gives you anti-time ordered OT21, OT2. Okay? So I just give you something like this. So now if you look at all this ordering, write it explicitly, then you find that this is just given by I theta T1 minus T2 commutator O1, O2. Okay? Commutator O1, O2. So this precisely gives you the retarded Green function. So this precisely gives you a retarded Green function. So similarly, if you look at GAR, then that gives you the advanced Green function. And if you look at GRR, then that gives you a symmetric Green function, which is just 1/2 O1, say OT1, OT2. Okay? So that gives you a symmetric Green function. So that essentially covers all correlation functions at 2-point function level. Okay, all correlation function at 2-point function level.
We're just past 12. So
Okay, yeah, I will. Yeah, please give me maybe 2 more minutes. Yeah. Okay, so now we know. So now we know that actually this RA just gave you the basis in terms of the advanced and the retarded Green function. And the retarded Green function we know is a key for understanding physics, because the retarded Green function controls the linear response. Okay, so if you turn on some source, phi t, and then the response of this thing under this source, then is given by, say, at the linearized level, it's just given by retarded Green function with respect to the source. Okay? With respect to the source. Okay? So now, just do a little bit combinatorics exercise. Okay? You can generalize to all orders. You can generalize this to all orders. Turns out, it turns out the OT, now if you include the nonlinear, and so this is just GRA. Okay, this is just GRA, which we just derived here. So now it turns out if you do all, including all nonlinear response of this operator under the source, what you get is you get GRA phi t prime and plus GRA AA phi t prime phi t double prime, etc. Essentially, this set of index with RAA give you all the nonlinear responses. Okay, give you all the nonlinear responses. All the nonlinear responses. Give you all the nonlinear responses of this OT. Okay. So now you can ask, what happens to? So it turns out. So now in the statistical system, what you are interested in, you are interested in OT. Also, you are interested in the fluctuation of O, say the second moment, and the third moment, etc. Okay. And we see that the second moment, the 2-point function, symmetric 2-point function, which controls the fluctuation of O, is actually given by the GRR. Okay? Again, these patterns continue. All these different moments, they are just related ON. Yeah, let me just heuristically write ON. They just can be captured by G, R, R with NR. And now you can ask, then what is the interpretation of the GRR with some number of A? And that gives you the response of this moment to the sources. Okay. So for example, yeah, just let me. Sorry, just give you 1 more minute. So for example, the GRR just corresponding to the symmetric green function. So now GRRA give you now GRA. So now you can consider this symmetric green function. Sorry. OT1, OT2, symmetric green function under the source, and then turns out that give you GRR. So leading order give you just GRR, and then the next order give you GRRA source, and the next order give you GRRAA the source, etc. Okay. So now, in fact, so this set of correlation functions observable in fact give you all the higher moment fluctuations and their responses, and the response of the fluctuations to the sources. Okay, and that actually incorporate almost anything which one can measure in the real lab. So that's why this quantity. So that's why this generating function is already enough to capture most of the physics we are interested in. And so we will then build an effective field theory for this quantity. Okay, so that will be our analog of the partition function for the line equivalent system. Yeah, thanks.
Maybe a quick question before that? You said you're working with an analog of the
Yeah.
equilibrium system. Is there any advantage or just identifying that with the relative entropy with the equilibrium state?
Oh, so there is non-equivalent definitions which people define this. In particular, in quantum information community, people define this non-equivalent free energy. But they always have to rely on the system coupled to a constant thermal mass, and then they can define this analog of non-equivalent or free energy. But that's not the most general thing. Yeah, that can define. That's a non-equivalent free energy, and it's not like free energy for the equivalent case, which really essentially covers everything. And in the non-equivalent case, you can have many different definitions, and then they maybe capture some physics, but not other physics. Yeah, there's no such universal quantity which captures everything.
There's one more, and then we'll go.
Yeah.
Purely A, the functions vanish.
Yeah, that's a good question. All the AA function vanishes. You can just easily show just from kinematics. Yeah.
And if you add more contours, do you get like out of time order functions?
Yeah, exactly. So now you can ask. So here I'm talking about the moments. We are talking about the moments and the response of those moments. But you can also ask. Suppose we are interested in the fluctuations of the commutator itself. So suppose we are interested in the fluctuation of the retarded green function itself. And then that is not captured by here. And that you have to use 4 contours. Yeah. And again, when you include the more and more contours, then that captures the higher order of this kind of fluctuations of your higher responses, etc. Yeah.
Yeah. All right, great. Let's thank Tom again. See you all at 2 p.m. for primordial cosmology. It's very interesting talk. I enjoyed that.
Thanks.
Final Friday.